Good morning. I welcome you all to this session of fluid mechanics. So, this class I will start a new section, conservation equations in fluid flow. But before that, as usual, I like to have a closure of the earlier section, kinematics of fluid, and before and even prior to that, I like to continue with two more problems, because last class, due to the lack of time, we solved only one problem. Two very simple problems we go through hurriedly, and then with a quick closure of the earlier section, the kinematics of fluid, we will start the new chapter or new section, that is conservation equations in fluid flow. So, let us go to a problem related to earlier section, that is kinematics of fluid. So, just a simple problem, the straightforward applications of our theory. The velocity components in a two-dimensional flow field for an incompressible fluid are given by u is this, v is this. U is e to the power x cos hyperbolic of y, and the y component of velocity minus e to the power x sin hyperbolic of x. Determine the equation of streamline for this flow. So, it's a very straightforward application for the equation of streamline. As you know, the equation of streamline is that dy dx, if you recall, for a two-dimensional flow field, the equation of the line, which is the streamline, represents the velocity vector as the tangent at every point to this line, is given by v by u. So, this is the equation of streamline. So, fluid mechanics ends here. What remains is a simple school level mathematics, that is dy by dx or dy dx, as you tell, is v by u. That means minus, what is that, sin hyperbolic x by cos hyperbolic y. So, if you make it like this, sin hyperbolic x dx, okay, plus cos hyperbolic y dy is 0. So, if you integrate this, this is the differential equation. If you integrate this, you get the form like this. What is the integration of sin hyperbolic x dx? Cos hyperbolic x, and this will be sine with the same sign for the hyperbolic function, and that will be a constant, integration of 0. So, this is precisely the equation in the xy plane for streamline. This is precisely the equation in xy plane for this streamline. So, these constants, the values of this constant can be found out if we define the streamline, that this constant value for a given value of x and y. This we will come afterwards when we will introduce the concept of stream function. So, the constant will represent a parameter, that means a series of curves representing the streamlines with different values of this constant c, for example, as the parameter. This is a very simple straightforward application. Another straightforward application for, in kinematics of fluid regarding the fluid motion, you see a three-dimensional velocity field. As you know that I told yesterday, the three-dimensional flow means where the three components of velocity exist, and all the three components are functions of x, y, z, all the three space coordinates in general. So, this is known as a three-dimensional flow field, which is given by the u component, x component of velocity. Of course, here is not a function of z, x, y and u0. This u0 is a constant. This is defined in the problem. Y component of velocity is given by this, and z component of velocity is given by this. In this equation, c, w0 and u0, these are the constants. C, w0, u0, these are the constants. So, variables are x, y, z as the independent variable, and dependent variable are the velocity components u, v, w, which are function of x, y, z. This is a steady velocity field, as we see, because there is no dependence with time. So, what we have to find out, find the components of strain rates and rotational velocities. It is again a straightforward applications of the fluid kinematics, that how do you define the strain rates? Let x coordinate strain rate is epsilon x, which is given by del u del x. Epsilon dot y, that means the rate of strain in y direction, that means these are the gradient of the velocity components in that direction with respect to the space coordinates in that direction. So, it is very simple to remember. The strain rate in z direction is the differential of z direct component velocity with z. So it is a simple now class school level thing that del u del x is c. So it is c. Well, what is del v del y? Again c. So it is a constant strain rate in y direction. Del w del z is minus 2c. So these are the values of epsilon dot x. Straightforward application. Epsilon dot z. हो गया? Fine. Next is the shear rate or angular deformation, rate of angular deformation, angular strain rates, whatever you call. We know gamma dot xy in the xy plane, it is del v del x plus del u del y. Similarly, gamma dot xz plane, what will be the value? Del w del x plus del u del z, all right. And well, gamma dot yz is equal to what? Gamma dot yz is del w del y plus del v del z. All right. Now what is del v del x? Now a straightforward substitution, it is 0. V is not a function of x. But del u del y is not 0, it is twice w0. That means it has got a fixed angular strain rates in xy plane which is twice w0. Similarly, for xz plane, del w del x is 0 since w is not a function of x. Del u del z, it is also 0. That means it doesn't yield any angular strain rate or deformation rate or shear rate. These are the terminologies used in the xz plane. Similarly, if we inspect the angular strain rates in yz plane, del w del y is 0, del v del z is 0. That means it has got only strain rates in xy plane. Now again, if we think of rotation, it is very simple. Rotation, the same application, but here a sign convention comes. That means if you take this as x, y, z, probably you recall I discussed it in the class that the omega dot x, that means the rotation about the x-axis, that means in the yz plane, will be half. The positive sign is this. That means del w del y minus del v del z. Okay. Then omega dot y will be similarly half del u del z minus del w del x. Well, similarly, omega dot x will be half. This was derived in the last class, del v del x minus del u del y. That means about any axis, it will contain the velocities in the components not in that. The next about rotation about x-axis will contain the z and y component velocities, and they are cross differential. Z component with y component with z with a minus sign. So it can come from the determinant concept, as you know, I, j, k, that is del del x. Again I am repeating this thing, del del z, u, v, w. That means this is the curl of the velocity vector. This is the definition of half, of course, is there, half, of course, is there. So from here analytically one can find out. Now the next part is to substitute the value accordingly, and you can find out the values. That is left to you. That's simply substitution of the value as I did for this strain rate. So this is the formulae, and you can find out. So this is all for the examples which I like to show you in this class. Now I would like to give you a close-up, hurried close-up of the chapter 3, that what we actually observed or read in chapter 3. First is it is the fluid kinematics. First, there are two approaches to describe the fluid flow. One is the Lagrangian approach, which considers each and every fluid element of given identity and to trace their path in the fluid flow. The identity is fixed by fixing the position vector of a fluid element at a given interval of time. So therefore, at a particular interval, at a particular instant of time, Whereas Eulerian approach solves the fluid flow problem by concentrating at a particular point and describing the flow velocities at that point as a function of time. So therefore, in an entire flow field, the velocity field is described, or the acceleration field is described as a function of space coordinates and time. So Eulerian approach describes the velocity, acceleration and all hydrodynamic parameters as a continuous function of x, y, z and t. That means the space coordinates and time. And this is the most convenient way of defining a fluid flow. Then we recognized what is a steady flow and what is an unsteady flow. When all hydrodynamic parameters become independent of time in a flow field, the flow is said to be steady. And if it does not do so, the flow is an unsteady flow. Similarly, a flow is said to be uniform when the velocity and accelerations in a flow field are independent of the space coordinates. They are same at each and every point in the flow field. So this is known as the uniform flow. The flow in general may be unsteady and non-uniform, but any combinations of these four can occur. Next, we appreciated a very important thing, that is the acceleration. The basic thing is like that, when any parameter changes because of the time and also due to convection. That means a parameter is changing because of the convection, the parameter is convected. So the time and the convection both are coupled to make the change of the parameter with time, because that parameter moves with the flow field. So therefore, with time it has got a movement. So therefore, the change composed of change with respect to time at a given point, if you restrict the movement, plus the change along with the convection. A simple example is that if a fluid particle, if we trace its change in velocity with time, then as the fluid particle moves with time, its change of velocity will depend because of its movement from one position to other position along with the change in the velocity field even at a particular position with time. So in general, therefore, this is the rule that a total derivative with respect to time contains a temporal derivative, which is the change with respect to time at a fixed point plus the convective derivative. So this gives the concept of temporal and convective acceleration. So total acceleration or substantial acceleration consists of two parts. One is the temporal acceleration, which is the change of velocity at a point with respect to time because of the unsteadiness in the flow. And another is the convection, that is the change of velocity even for a steady flow, for a fluid particle moving from one point to other because of the non-uniformity of the flow. So therefore, temporal acceleration plus convective acceleration is the total or substantial acceleration. Then we recognize streamlines, path lines and straight lines. Streamlines are imaginary lines drawn in a fluid flow so that the tangent at any point on this line represents the velocity, direction of the velocity vector at that point. Now, the series of streamlines changes from time to time for an unsteady flow. The path lines are the locus of the different fluid particles with different identity. And straight lines we have defined as the locus of the fit or the end points of several points, several fluid particles that have crossed a particular point, fixed point. So a straight line specified by that fixed point through which a number of particles have crossed, and at a given instant what are the end points of those particles along their locus. This is a straight line. In steady flow, streamline, path lines, straight lines are coincident, since the Lagrangian version and Eulerian versions become identical. Then the most important part, and that is the last part of that section, which we recognize that a fluid particle in general have three distinct features. One is translation. Simple translation is translated without changing its shape, without changing any dimensions, linear dimensions of the body or angular dimensions. Plus rotation and deformation. Deformation is the most distinguishable feature or most important feature that distinguishes a fluid element from a solid element, that fluid in continuous motion continuously deforms, is getting deformed its shape. The shape gets deformed continuously. And the dimensions, linear dimensions and angular dimension goes on changing continuously. So fluid elements have got three distinct parts, one translation, rotation and deformation, whereas a solid body has translation and rotation without deformation. That means for solid body, if it is translated without any change in the linear dimensions or angular dimensions of the body. Dimensions remain as it is. Similarly, when fluid body gets a rotation, its dimension remains same. That means all the particles in the solid body, all the particles of the solid body moves with the same angular velocities. So solid body does not have the deformation, which is the distinguishable feature for a fluid body in its motion. Okay, now with this I close the lecture on kinematics of fluid. Today we will be discussing the conservation equations in fluid flow. Now you know that any physical system under any process transferring energy, exchanging energy, or any process which is performed by any physical system must obey three laws of conservation. One is the conservation of mass. That means mass is neither created nor destroyed. Mass of a system remains unchanged. Another is the conservation of momentum that you have already come to know from your school level, that conservation of momentum is given by the Newton's second law of motion. The momentum should be conserved with respect to the force applied on a system according to the laws of motion. Another is the conservation of energy. Energy is neither created nor destroyed. So if there is any conversion of energy, transformation of energy, total energy remains unchanged. Of course, one thing has to be told here with caution, that there are physical processes where mass and energy is being mutually converted to each other. So if you take care of those processes, these three conservation equations are not independent. For example, the conservation of mass and conservation of energy then jointly make a conservation statement, that conservation of mass and energy, that means mass plus energy remains constant. However, if we discard that particular part of the physics with which at present we are not interested in our fluid flow problem, where the mass energy mutual exchange is there, we can tell that three independent laws of conservation or conservation laws, that conservation of mass, conservation of momentum and conservation of energy, have to be followed or obeyed by flow of fluid also, as it has to be obeyed by all physical systems under any conditions or executing any process. Now, before examining these all three conservation equations, our main objective of this chapter will be to apply this conservation equation to a fluid flow problem and finally derive an equation relating its hydrodynamic parameters like velocity, pressure and all these things. And we tell that this is an equation relating to velocity, pressure, which comes from the conservation principle, either conservation of mass and conservation of momentum and conservation of energy, and we give a name to that particular equation. But to derive those equations following the conservation principles, we first know certain terminologies which will be very helpful in studying solid mechanics. Of course, you have learned it in solid mechanics, fluid mechanics, thermodynamics, any physical system to learn, we must have to know some terminologies. Let us concentrate on those terminologies. Okay, now what are those things? How do you define a system? How do you define a system? Now, a system is usually defined as some amount of mass of the working fluid or working system, some amount of mass within a given boundary. So system definition includes two things, some amount of mass and some boundary. Boundary is very important for defining a system. So a system distinguishes a given mass with a given boundary. So boundary is very important for this system. So system has two important characteristics. One is the mass and another is within the boundary. And everything external to the boundary is known as surroundings. Surroundings. So this is the definition between this is a system and this is a surrounding. So surrounding is everything external to this system. There may be another system. For example, we can think of system A with a boundary and system B interacting between each other. In that case, if we tell system A as the system, system B will be surrounding to the system A. Similarly, system A will be surrounding to system B. So surrounding means it is external to a particular system on which we are paying our attention. But now with this characteristic feature, we can tell there are two types of system, which is very important. One is control mass system. Control mass system. You will get in my book, but I tell you that rarely in any book it is defined like this. Control mass system, or sometimes we call it that closed system, or in a more liberal way, convention, we call this as the system. Then you can ask me, sir, then other type of system you have told to, that is not called system, usually not. So this I am coming chronologically. It is basically control mass system, another is control volume system. One is control mass system, another is control volume system. So control volume system we sometimes define as open system. or we sometimes define as control volume. We don't refer to system. So when system and control volume, the two words are defined, system refers to control mass system or sometimes closed system, and control volume system sometimes defined as open. Control mass system goes with control volume system vis-a-vis. Comparison is very clear. Closed system and it is open system. And one is system. If this we call system, this we call simply control volume. What is the difference? In a control mass system or closed system, this is the boundary of this system. The restriction is that there is no mass flow, M is 0. There is no mass inflow or mass outflow to the system. Only energy inflow and energy outflow is there. Energy may either come in or energy may either go out. So system boundary does not allow any mass to come in or go out, which means that in a closed system it is not only the amount of mass M, but its identity remains same. That means the same mass with the same identity remain within the closed system. Closed system does not allow the mass transfer, so mass does not come in or go out. So boundary of a closed system may expand, may collapse because of the mechanical work done. There is no restriction for the volume of the closed system, but boundary may expand or collapse without allowing any mass to come in. Boundary may be fixed, it may not expand and collapse, it may receive only heat or it may reject heat. So any form of energy transfer across the boundary is possible. Whereas in a control volume system, so therefore you see this is known as closed system, it is closed, it is not allowing any mass, and it is referred to as system sometimes, only system. Whereas in a control volume system, simply we tell is that sometimes control volume, the mass transfer is relaxed. That means there may be mass coming in and there may be mass going out. Some portion the mass may come, some portion mass may go out. Along with the energy. So both mass and energy inflow and outflow takes place. But here the restriction is that this boundary is rigid. That means this boundary does not move. That means in a control volume the volume is fixed, whereas in a control mass or closed system the mass is fixed. That's why this is known as control mass system, and that's why it is known as control volume system. But in a control volume mass may come in, mass may go out. So therefore as far as the mass of the system, the control volume characteristics is that the identity of the mass changes. That means at some condition the mass may remain same in the control volume, that the amount of mass coming in exactly equals to that out. But still in that case control volume system or open system or control volume differs from the closed system is that it is not only the mass but the total identity of the mass remains same. You understand? So here the identity is lost because the mass is going out also and coming in. Mass may or may not remain same depending upon the balance between inflow and outflow, but identity is always lost. So this is the closed system and the control volume or open system. Another type of system also we define, which is isolated system. Please write isolated system. So this system is very simple. So this is control mass system or closed system or system. So sometimes we will refer only by system, and this is control volume system, or simply we will refer by control volume system or open system. Isolated system by definition is isolated in all respect. That means isolated system is a passive material. That means they are isolated. That means there is neither mass interaction nor energy interaction. That means an isolated system does not interact with the surrounding, while a closed system interacts with the surrounding in terms of the energy transfer. A control volume system interacts with the surrounding in terms of both mass and energy transfer. This is the surrounding external to the system, while an isolated system is isolated from the surroundings in all respect. That means neither mass transfer nor energy. That means total energy and mass even with the identity remains same in an isolated system. It doesn't change with time. So these are the three terminologies, that closed system, open system or control volume, isolated system, which will be required afterwards in describing other many hydrodynamic parameters and analysis of many engineering problems. Now let us see what is continuity equation. Continuity equation is, now first of all we start conservation of mass. Conservation of mass in fluid flow. conservation of mass in fluid flow. Fluid flow. If we apply the conservation of mass in fluid flow, as we know, the closed system, if we apply it to a closed system, you can tell me, sir, what is great in it? If the mass of a closed system is 0, the conservation of mass is given by this expression, dm dt is 0. But this is not true for an open system or control volume. So what is then with respect to an open system? What is this with respect to an open system or control volume? Please tell me. What is this with respect to an open system and control volume? The mass of a closed system is 0. If we have an open system or control volume, so we can simply tell the conservation of mass like that. If the mass enters to control volume, this is the mass flux entering and the mass flux leaving. Mass flux leaving. What should be the general statement for conservation of mass for a control volume where the mass flux coming in continuously and mass flux leaving continuously? Can you always tell that the mass flux leaving is equal to mass flux entering? We cannot always tell. This we can tell at a particular condition when the control volume mass will not change. So this is a particular condition. Control volume may absorb mass, that means the mass may remain within the control volume, or control volume may lose mass, some mass may go from the control volume. So the most generalized statement relating to that is the net rate of increase, let us consider increase in mass in the control volume plus net rate of mass efflux from the control volume is equal to 0. It comes from basic intuition. So that net rate of mass efflux plus net rate of increase in mass in the control volume is 0. That means net rate of increase in mass in the control volume is the negative of net rate of mass efflux. That means the net rate of mass influx. That means mass influx minus net rate of mass efflux means mass efflux minus mass influx. So one can see from very common sense that rate of mass influx minus rate of mass outflux is the net rate of increase in mass in the control volume. So therefore this is written like that. When the net rate of increase in mass in the control volume is 0, that control volume does not increase its mass or decrease its mass by this mass transfer processes, then net rate of mass efflux from the control volume is 0, or net rate of mass influx, which you tell with a positive or negative sign, is 0. That means the rate of mass influx and rate of mass efflux is balanced. So the statement of conservation of mass applied to a control volume or open system, this is the very basic thing which comes straight from the common sense, is utilized in deriving an equation. That means this constraint of conservation of mass is utilized with respect to a control volume in deriving an equation relating the velocity field in the flow and known as continuity equation. So continuity equation is an equation which is derived by using the conservation of mass with respect to a control volume. Let us derive the continuity equation. Okay, all of you have understood? Now let us consider a XYZ coordinate axis. I have given x in this direction. Okay, let us consider this as y and this as z. Now, with respect to any frame of reference, if we like to define the continuity equation, that conservation of mass applied to a control volume, first step is that you define a control volume whose planes are parallel to the coordinate planes. That means here I define the control volume like this. I define a control volume like this. Okay. I am not drawing in the spirit of the drawing actually, this will be dotted. So this is a parallelepiped. So if the first step is to derive, for example, deriving the continuity equation, again I am telling, with respect to any frame of reference, first step is to draw the control volume whose planes are perpendicular to the coordinate planes. So therefore, in a Cartesian coordinate system, it will be a parallelepiped. Okay, let us give this name A, let this B, C, D, this is E, F, G, H. Now we define a control volume with imaginary boundaries, because the boundary of a system or control volume is not necessarily to be a real and rigid. It is an imaginary boundary which one can choose depending upon the need of the problem. And let the dimensions of this be dx in the direction, this length, along with the coordinate direction convention dy, and let this is dz. That means this one is dz. Well, now we should find out how the mass flux is coming in. Let us consider the u component of velocity, that is a positive x direction, v component of velocity in the positive y direction, and z component of velocity in the positive z direction exist in the field. So therefore, with this positive x direction velocity, there is a mass flux coming across this plane AEHD. This plane we call it x plane, as if, why? Because the normal to this plane is x direction. That means x plane, there are two x planes, AEHD and B, what is this? ABCDEF. This is BFGC. So through this x plane AEHD, let us consider a mass flux m dot x is coming. So due to this typical velocity field, the mass flux m dot x plus dx, we consider this mass flux changes over a distance dx as m dot x plus dx, which is nothing but the mass efflux across this x plane. That means BFGC, which is dx distance apart from this x plane in the positive direction. So what is mx dot? That is mass flux coming in to the control volume through the phase AEHD. You know, the volume flux in a fluid flow is given by the velocity times the area. So if the velocity is u, what is the area? Area is dy dz, dy dz. So dy dz. And volume flow times the density is the mass flux. So mass flux is simply rho u dy dz. That means u is the velocity. Velocity times the area is the rate of volume flow times the density is the rate of mass flow that is coming in. So the mass flow going out from the x plane, that means from the planes parallel to this x plane, that is BFGC, it is parallel to AEHD, which is going out, that will be m dot x plus dx. That means it will be m dot x plus del x of m dot x dx. And since dx is small, we can neglect the higher order term in the Taylor series expansion. So simply then we can write this is equal to rho u dy dz plus del x of rho u dy dz dx. That means del x of rho u dx dy dz. So this is the term extra over this. Now therefore, the net rate of a flux, because of this flow through x planes, there are two x planes. X plane means the plane parallel to yz plane. That means whose normal is x, is equal to del x. Net rate of a flux means a flux minus influx, del x of rho u dx dy dz. So this is the net rate of a flux into the control volume due to the fluxes crossing the x planes. Similarly, if we consider the fluxes crossing the y plane, let this is the fluxes crossing the y plane, So the flux which is coming into the control volume through the y plane, that means ABCD. So ABCD is the y plane through which the flux is coming in because of the velocity components v existing in this fashion. This is the positive direction of y. So let us consider this m dot y. Similarly, which is going out through another y plane which is parallel to this y plane ABCD. That is what? EFGH. That means this is this y plane perpendicular to the y axis. That we can designate as my plus dy. That means it is the change of the mass flux over a distance dy. Then we can write with the similar concept that my dot is rho times the volume flux, that is the flow velocity in this direction v, times this area dx dz. And with the similar notation, m dot y plus dy is m dot y plus del del y of m dot y dy. What we can write? We can write this is equal to rho v dx dz plus del del x of, del del y of rho v dx dy dz. So therefore, we can write the net efflux, net rate of efflux from the control volume, net rate of efflux from the control volume due to the fluxes parallel to the y planes is equal to del del y of rho v dx dy dz. Clear? In the similar fashion, we can do for the jet planes, that means the planes through which fluxes crossing through jet planes. That means there are two jet planes now. 4 planes we have considered, rest 2 planes are there. One is A, B, Fe and D, C, G, H. So fluxes coming in through this bottom plane because of the existing velocity component. So this is m dot jet. Similarly, fluxes going out through this jet plane dcgh, which is at a distance dz above this plane, and we just give it in value m dot jet plus dz. And in the similar way, we can write m dot z is rho w dx dy, the area of this plane. And similarly, we can write m dot z plus dz as del del z m dot z dz, plus m dot z, plus m dot z. So m dot z will come first. So this can be written as rho w dx dy plus del del z of rho w dx dy dz. So dx dy dz I can substitute as dv, that is the elemental volume of this control volume, dv. So that earlier also I can write it dv and I can write it dv. Now what I can write? Net rate of efflux in the control volume, due to the fluxes across all the faces, will be sum of this net rate of efflux due to fluxes across x plane plus net rate of efflux due to fluxes across y planes plus the net rate of efflux due to fluxes across z plane. That means sum of this I am writing as dv, sum plus this, sum of this and this. That means this is equal to del del x of rho u plus del del y of rho v plus del del z of rho w times dv, which is a common. Now what is net rate of increase? Because if we again recall our continuity equation, which came simply from physical common sense, net rate of increase in mass in the control volume, net rate of mass efflux from. So net rate of mass efflux from the control volume we have found out. But what is net rate of increase of mass in the control volume? Net rate of mass efflux. I am sorry, net rate of, every time I am writing mass efflux. What efflux? Mass efflux. Net rate of, I am sorry, mass efflux. So now net rate of increase in mass, net rate of increase in mass, net rate of, next thing we have to find out, of increase in mass, net rate of increase in mass within the control volume. What will be its expression? Within the control volume. What will be its expression? Within the control volume. What will be its expression? Its expression will be the rate of change of mass within the control volume. That means if I define the mass at the control volume at any instant, what will be that? Rho dv. And its change with time, control volume is fixed. So it's change with time. That means this is the mass of the control volume. This will represent this thing. That net rate of increase in mass within the control volume. That instantaneous mass of the control volume, its rho and its volume dV. So volume of the control volume, as I have told, by its definition is invariant with time. It will come out. So this is very important to know that how here V is coming out, dV, because of the definition of the control volume. So according to this statement, physical statement, now I can write del rho del T plus del x of rho u. So according to the conservation of mass applied to a control volume in a Cartesian coordinate system, we can write this into dV is equal to 0. True? And this is valid for any value of dV. It is irrespective of the volume of the control volume, which is an arbitrary parameter, which means this quantity has to be 0. Okay, because dV is not 0, it is valid for any value of dV. Any finite volume of the control volume, this quantity has to be valid. So finally, therefore, we can write this as the continuity equation, del rho del T plus del x of rho u. So in a Cartesian coordinate system, so this is the continuity equation. That means in a Cartesian coordinate system, the consequence of conservation of mass or application of conservation of mass in a control volume gives an equation which is known as continuity equation. This continuity equation form, this is the continuity equation in Cartesian coordinate system. Del rho del T plus del x of rho u plus del y of rho v plus del z of rho w is equal to 0. So when a special case now we consider that when the fluid is incompressible, for an incompressible fluid or for an incompressible flow, we are not interested fluid is incompressible or compressible. We have already recognized earlier that whether the density changes in the flow or not, we are interested. For the flow where density does not change, it is an incompressible flow where the Mach number is below 0.33, then density is invariant. Nowhere in the flow field density changes, density is not a function of x, y, z, and similarly this becomes 0 and this comes out. So therefore the equation becomes del u del x plus del v del y. So it is very important that for an incompressible flow where density is neither a function of time or nor a function of x, y, z, in a Cartesian coordinate system with u, v, w are the respective velocity components along x, y, z direction. This is a special case of continuity equation for an incompressible flow. All right? Okay. So today up to this, well, next class we will discuss again in continuation to this. Okay, thank you.